Hello, how's it going? In today's video, we're going to be tackling a very hard integral that deals with basically combining two techniques of integration. So we'll be evaluating this following integral, the integral from 0 to infinity of sine squared x divided by x squared multiplied by x squared plus 1 dx. Now this is a very hard integral to evaluate. But we're going to do it in this video. I don't know how long this video will take, but we're going to solve this. We're going to evaluate this from 0 to infinity. So the way we actually do this is basically we're going to change how this integral looks and then do complex analysis on it. So we're going to combine Feynman's technique of integration with complex analysis. So we're going to use Feynman's technique straight up to make this integral a bit easier to do. So basically we're going to differentiate under the integral sign. So what we do straight up is basically make this integral basically a function of a different parameter. So we'll just say, all right, f of alpha is equal to the integral from 0 to infinity sine squared of, and we'll put the alpha here, and of course the bottom bit, so x squared multiplied by x squared plus 1 dx, okay? So that's the first bit. We put in a new parameter. So alpha is independent of x, so it's some real parameter. So now all we're going to do is find f dash of alpha. So the way we do that is basically we're going to differentiate both sides. So all we got to do is just write, all right, f dash of alpha is equal to the derivative with respect to alpha of this entire integral. So 0 to infinity of sine squared alpha x divided by x squared over x squared plus 1 dx. Now basically all we're going to do is bring this on the inside, but when we do that we can basically turn this into a partial derivative. Now there's a proof for that somewhere in one of the pages of this book. It's in Advanced Calculus. It's one of the books Richard Feynman used when he was in college. It's how he learnt this technique. That's why it was kind of named after him, because he basically learnt this technique of basically putting this on the inside, making a partial derivative, and that's how it got the name Feynman's technique, because he basically took this technique from an old book and it got really popular. So we can actually put this on the inside and turn to a partial derivative, and then once it's a partial derivative, x becomes a constant and we can only differentiate with respect to alpha. So f dash of alpha is equal to the integral from 0 to infinity of the partial derivative with respect to alpha. So x now becomes a constant. So we're only differentiating this bit here with respect to alpha. So as you can see on the top is the only bit where we have the alpha. So the entire bottom of this fraction is useless to me. So when I'm differentiating, I'm only looking at the sine squared alpha x. Okay, so recall if we have sine squared of ax and you're wanting to differentiate that with respect to x, okay, what would you do? Of course, it's going to be like the chain rule, because sine squared of x is basically this, sine of x all squared. They write it like this for shorthand because they're too lazy. That's why they put the little square here. And that confuses some people because they think, oh, is it like this bit? No, you have to have sine of something. This sine squared, oopsie daisy, rub that bit out. Let's put that back. This sine squared means this. It means sine x all squared. So when they write it like this, it's just shorthand. So the way we do this is basically, all right, got to do it by chain rule. So we bring the power down the front, multiply it by the function again, and then we differentiate the inside function with respect to x. So it's going to be a cos of ax. Okay, so that's what happens when you differentiate this with respect to x, and let's say a was a constant in this case. So let's just rub that out now. And now let's take a look at what we have down here. So we're doing the exact same thing. So we're finding the partial derivative with respect to alpha of sine squared of alpha x, pretty much. So what we're going to do is bring this 2 down the front. So we're going to have equals to 2 sine of alpha x. Now we're going to differentiate the inside function with respect to alpha. So the x is our constant. So that constant comes out the front. So we have x cos of alpha x. And that's how you differentiate that bit. So when we go down here, so let's just move this all down here. So when we rewrite this now, so we can write f dash of alpha is equal to the integral from 0 to infinity of, what did we say it was? It was 2 sine of alpha x cos of alpha x, okay? And of course we still have the x squared multiplied by x squared plus 1 on the bottom. This was not effective because there's no alpha down here, so the x is just treated as a constant. That's why we have partial derivative. Okay, so we know that we're only differentiating with respect to the other variable. Now you can notice this here cancels with one of these, so we can actually simplify this even more and say, all right, f dash of alpha is equal to the integral from 0 to infinity of 2 sine of alpha x cos of alpha x divided by x over x squared plus 1 dx. Now, this is where a little trick comes in. So there's a trigonometric identity that says if you have 2 sine of a multiplied by cos of a, that's equal to sine of 2a. Now, if you made this connection straight away, that's great. But now I'm just going to point out this trick to you straight away. So we can apply that down here. So we can rewrite this whole thing as f dash of alpha is equal to the integral from 0 to infinity of sine of 2 alpha x over x squared plus 1 dx. Now, this is where the Feynman's technique of integration takes a bit of a pause. Now we're going to do complex analysis. So we've changed the way our integral looks a lot. We've got f dash of alpha to looking like this. Now this is something we can handle using complex analysis. Okay. So what we do straight off the back is basically we basically define this as a complex function. So we say let f of z equal, and we replace trigonometric terms, so sine and coses, with Euler's formula. So e to the power of what is it? Yep. So e to the power of 2 alpha I z. Yep. Then you replace the x's with z, so you have z over z squared plus 1. Cool. Righto. Now we're going to basically integrate this over a contour. So when we're looking at this down here, we have to look at the pole. So we have a pole. So the poles, pretty much, we're going to have to use the residue theorem with complex analysis here, because we have a singularity at z equals 0. We have a residue at z is equal to, that's what we have to do. Okay, so basically we want to factorize the bottom bit. So basically we're going to rewrite the top. So e to the 2 alpha I z over z, and we basically want to factor this into basically the factors of I. So z squared plus 1 is the same as z squared minus I squared, because I squared is -1, and then if you put the -1 there, you're going to get plus 1. So we can rewrite this as this, and this is just the difference of squares. So we can write this bottom bit as basically z plus I multiplied by z minus I. Okay? The reason we've done that is it's basically going to tell us where the poles are when they're integrating over our contour. Okay? So let's just make note. Our poles, when z is equal to 0, z is equal to I, and z is equal to -I. Okay? Because we know that from the bottom here. Now we're basically going to integrate f of z over a contour, so we're going to choose a semicircle in the upper part of the convex plane. So let's just draw basically an Argand diagram. So this is our real axis, and this is our imaginary axis. Okay, and I'll just denote it with a z there, and I'll denote this here with an x. Okay, so basically we're going to integrate from basically some huge value r, and we're going to say r is strictly positive. Okay, so it's greater than 1. Okay, and we're going to integrate it all the way to -r over here. So we're going from r to -r, and then we're going along here. Of course, we have a singularity at z equals 0, so we have to make a little detour around here. So we're going to have, let's say, -epsilon and to epsilon, and they're like really small numbers over to here. Okay. Alright, now we're going to basically draw our residues are. So we have a residue at z equals 0. We have one there. We have one at z is equal to negative I. That's down here somewhere. And we also have one in our contour. So we have one in here. So let's just say this path here is capital gamma. And let's say this path here is capital lambda. And this is a contour C. This is our contour. We're integrating over here. Now, basically we're going to have to say, all right, the integral of our contour over the path C of f of z is basically we can break it up into its parts. So we have the integral from negative r to negative epsilon. So we're going to have integral negative r to negative epsilon. And of course that's on the real axis, so we'll just have that as f of x dx plus the integral from negative epsilon to epsilon, which is the path capital lambda. So the integral from capital lambda over capital lambda, that's a terrible way to draw it. So that's a huge integral as well. The integral from capital lambda over, and of course this is in the imaginary plane now, f of z dz plus the integral from epsilon to r in the real axis, so f of x dx. And I probably should put the gamma one at the front because we're starting from here and going around here. Plus the integral over the path capital gamma of f of z dz. Now we have a pole in our contour, so this is equal to basically the residue theorem. So we can rewrite, integrating over our contour of f of z dz is equal to 2 pi r multiplied by the sum of the residues of f of z. Okay? Now, we need to calculate our residues. Now, as you can see from my diagram up here, we only have one, and that's when z is equal to I. Okay, that's this one. Oh, my cord went on my drawing pad. That's here. It's somewhere in our contour, because we don't know how big this curve is, but we know it's somewhere in here, and r is strictly positive, so it's like a huge number. Okay, so the way we calculate our residues, we'll calculate the first residue, or the only residue. So the residue, when z is equal to I of f of z, we say, that's equal to the limit as z goes to I of z minus I multiplied by f of z, which is just going to be, in this case, I think it's, what did I say it was up here? It was, e to the power of 2 alpha, e to the power of 2 alpha I z over z plus I and z minus I. Okay, so this is how we calculate one of the residues, and as you can see, that cancels with that, so we're just left with the limit of this little thing in here. And if we evaluate this limit, we're going to have e to the power of 2 alpha I squared over I plus I. So that simplifies down to negative 1 over 2 e to the 2 alpha, because this turns into a negative 1, and using an indecimal, so we flip it down here. This turns into 2i, and then you multiply that by I, and you're going to get negative 1, so you get negative 2. That's where that comes from, and we just moved it up there. So that's where all that evaluates to. So now we substitute this bit into here pretty much. So we can say our integral over our contour path C of f of z dz is equal to 2 pi I multiplied by negative 1 over 2 e to the 2 alpha. The 2's cancel, so we're left with negative I pi over e to the 2 alpha. Now, the beauty about this thing here is basically this whole thing is equal to the sum of our parts up here. So we can basically put this, oopsie daisy, what did I do there? We can basically put this thing here is equal up here. So now we're going to move these integrals down the bottom here, okay? So we have the integral from, integral from over gamma. So we have integral over capital gamma of f of z dz plus the integral, I'm just going to put our complex bits together, of capital lambda of f of z dz plus the integral of, what was it, negative r to negative epsilon of f of x dx plus the integral from epsilon to r and f of x dx is basically equal to negative I to the pi over e to the 2t. Alright, what are we going to do now? This looks nothing like our integral that we started with all the way up here. Well, I'll tell you, we're going to get to it. It's just going to take a while. So, obviously we want to turn the real parts into pretty much, we want a sign to pop out. So the way we can do this is basically, you can see this integral here and this integral here nearly have the same bounds. If they get the same bounds, we can put them together. So let's just take a look at this single integral here, and let's basically change its bounds so it fits in. So this integral is the integral from negative r to negative epsilon of e to the, what was it, 2 alpha I x over x squared plus 1 dx. Okay, now we're going to use a dummy variable. Now a dummy variable basically means is whatever this integral evaluates to, it's going to be independent of the variable, so you can pretty much do whatever you want there. So basically we're going to just say, alright, let x equal negative u. So therefore if you differentiate here, dx is going to be equal to negative du. Therefore, if you put this bound into here, you're going to get positive r. So we're going to have the integral from r to epsilon. So these bounds change because when we substitute them into here, they turn to positive. Then we're going to have e to the negative 2 alpha I u over this is going to be negative u, and then go negative u all squared plus 1 multiplied by negative du. So that cancels, that turns into a positive. So we're left with the integral from r to epsilon of e to the negative 2 alpha I u over u multiplied by u squared plus 1 du. Now we're going to switch these bounds and just put a negative sign at the front, so we'll put a negative there and just change the position of the bounds. So the epsilon goes to the lower bound and the r goes to the upper bound. Okay, and since this is a dummy variable, we can basically just turn it back into x now, because it doesn't really matter. Whatever this evaluates to, it'll be independent of whatever variable it is. So we're just going to move this whole thing now to the side, because it's not really helpful to us anymore. So move that over there, and we'll move this over here. So now we can combine our integrals up here that we've already established together, because they're going to have the same bounds now. So we can say, alright, the integral over the path gamma of f of z dz plus the integral over the path capital lambda of f of z dz plus the integral from epsilon to r. So I'm just going to combine these integrals now. It's going to be e to the power of 2 alpha I x minus e to the power of negative 2 alpha I x over x multiplied by x squared plus 1 dx is equal to negative I pi over e to the 2t. Okay? So now what we're going to do is basically, alright, the definition of sign in complex variable is, alright, sine of x is equal to e to the ix minus e to the negative ix over 2I. So therefore we're looking for sine of 2 alpha x, aren't we? So that should be equal to e to the power of 2 alpha ix minus e to the power of 2 alpha ix negative over 2I. So you can see we already have that almost, so we just got to put this 2I to the other side, and then we can pretty much substitute that. So we're going to have the integral of the path gamma f of z dz plus the integral over the path capital lambda f of z dz plus we're going to have this 2I come out the front, so we'll have 2I over the integral from epsilon to r sine of 2 alpha x over x squared plus 1 dx. Cool. Now, this is almost like our integral that we established before. So once we find that, we can basically turn it into the integral that we wanted to evaluate at the start of the video. Oh, this is also equal to, what was this equal to? This is equal to negative I pi, what was it up here? E to the power of 2t. Okay. E to the power of 2t. Alright, so this is almost the same, except our integral has the bound 0 to infinity. So when you apply a limit to all these integrals, now if we apply a limit to the constant on this side here, it's not going to change, so we don't need to write anything on that side. But this integral and this integral here are going to change as we apply these limits. So if we apply, let's say, all right, r goes to infinity and epsilon goes to 0, okay? So we're going to have 2I over the integral of 0 to infinity of sine of 2 alpha x divided by x multiplied by x squared plus 1 dx plus, alright, this integral isn't affected by epsilon at all, but it is affected by r. So we just add, alright, the limit as r goes to infinity of the integral over gamma f of z dz plus this integral isn't affected by r but it is affected by epsilon, so we have the limit as epsilon goes to 0 of the integral over the path capital lambda f of z dz is equal to this constant here. We don't need to apply the limits because it's not bound to anything. The constant isn't going to change regardless if r goes to infinity or if epsilon goes to 0. So we just leave it as negative I pi divided by e to the 2t. We're using the entire Greek alphabet here, aren't we? Alrighty. Basically, we're going to now do some real hard stuff. We're going to prove that as this integral, as r goes to infinity, this integral is going to go to 0. Okay? That's the next part of this video that we're going to do now. Okay? So we're going to rewrite this whole thing. So now we're going to be like, alright, prove, because we recall on a little diagram here that r is all the way out here, and r is strictly positive, okay, on our little contour that we established earlier, okay? So just have this diagram in your mind, because as r goes to infinity, this semicircle is going to get huge, but it's actually going to evaluate to 0 as you integrate over the path gamma. So we're going to prove that as r goes to infinity over this integral over the path gamma of f of z dz, that this whole thing is going to be equal to 0. So what is this integral? So the integral over the path gamma of f of z dz is from r to negative r, isn't it? So it's the integral, sorry, it's the integral from r to negative r e to the power of 2 alpha I z over z multiplied by z squared plus 1 dz. This is our integral here. This is f of z over the path gamma. So now what we're going to do is basically make a substitution. We're going to say, alright, let z equal r e to the I phi. Okay? So it's in terms of like a rotation. And pretty much now, once we substitute this in, we're going to pretty much change what these bounds look like, and it's going to change how this looks and this looks and this looks, okay? So before we do that, we also need to find dz. So dz is going to be equal to r I e to the I phi d phi. Okay? So if we make this substitution, alright, what's this bound here going to be? So when r is equal to z, so we have r equals e to the I phi, that cancels, so we have 1 is equal e to the I phi. Now this is Euler's formula, so we're saying I is equal to cos of phi plus I sine of phi. Now what values of phi make this true? Well, if we have the value, let's say phi is equal to 0, this makes it true, doesn't it? Because this, cos of 0 is 1, and sine of 0, sine of 0 is 0. So this satisfies it. So phi equals 0 replaces when z is equal to r. What about when z is equal to negative r? So negative r is equal to r e to the I phi. So therefore negative 1 is equal to e to the I phi. So therefore negative 1 is equal to cos of phi plus I sine of phi. Now what value of phi works for this? So I'll tell you one shot at the back. Phi is equal to pi, because that turns that into a negative 1 and that turns that into a 0. So this satisfies it here. So our integral from r to negative r of e to the 2 alpha I z divided by z over z squared plus 1 dz turns into this. So this replaces when this goes down here. So we're going to have the integral from 0. This replaces this. This here, whoopsie daisy. This pi here replaces negative r, because we just did that with the change of bounds. So this pi goes up here. And now we're going to substitute the z in for what we established up here, this bit here. So we're going to have e to the power of 2 alpha I r e to the I phi divided by r e to the I phi multiplied by r squared e to the 2 I phi. I just squared that term, plus 1. And then you have your dz, which is r I e to the I phi d phi. That cancels with that, and that cancels with that. You're going to take this I out the front of the integral because it's just a constant. So we're going to have I over the integral from 0 to pi of e to the 2 alpha I r e to the I phi over r squared e to the 2 I phi plus 1 d phi. Okay? Now, all we're going to do now is basically we're going to estimate this value now. So we're going to let this integral equal to I. Okay? So basically, we're going to use like a triangle, like the direction of the path, the direct path is pretty much shorter than some detour. So the absolute value of I, which is our integral up here, is less than or equal to the absolute value of I over the integral from 0 to pi over the absolute value of all this pretty much. Okay, 2 to the r alpha I r e to the I phi divided by r squared e to the 2 I phi plus 1 absolute value d phi. Okay, so this is basically an inequality because the direct path is shorter than some detour. So the absolute value of this integral, when you have these on the outside, is less than or equal to the absolute value of basically the stuff on the inside of the integral. Okay, that's where that comes from. Alright, what's the absolute value of I? That's just going to be equal to 1. So we can I'm just going to start writing over here because we've run out of room. So we have I is less than or equal to the integral from 0 to pi. So the I just turned into a 1. So there's a 1 there. And then we can distribute this absolute values to the top and bottom. So we have the absolute value of e to the 2 alpha I r e to the I phi absolute value, and then we're going to have the bottom bit. Now, what do we do now? This just looks like an absolute mess. We're basically going to use the reverse triangle inequality to make this even simpler. So there's a formula saying if you have the absolute value of A minus B, it's going to be less than or equal to than the absolute value of A minus absolute value of B. Okay, this is the reverse triangle inequality. So we're going to take a look at this part here and try and put it in here. But of course you need a negative sign here. So we're going to fudge in a negative sign in there. So we're going to say, all right, r squared e to the 2I phi minus negative 1 is still going to be our thing in there, because negative 1 multiplied by negative 1 is positive. So we haven't changed anything, we just changed how it looks. And therefore we can use this inequality if we have this negative sign here. Is greater than or equal to the absolute value of our a bit, which is this bit here, which is r squared e to the 2I phi, absolute value, minus the absolute value of negative 1, which is 1. Now, the absolute value of this is just going to be r squared, okay? So we're going to have absolute value of r squared, oh, whoopsie daisy. Absolute value of r squared e to the 2I phi minus negative 1 is greater than or equal to the absolute value of r squared minus 1. Okay, and since r is strictly positive, we can get rid of these absolute value brackets. And now all we're going to do is basically flip this and take the reciprocal. Now, if you take the reciprocal of an inequality, you need to switch the sign. So 1 over r squared e to the 2I phi minus negative 1 minus negative 1, yep, absolute value is now less than or equal to than 1 over r squared minus 1. So as I flip this, I changed the sign of this. So this was pointing this way, now it's pointing that way, okay? So therefore, we can basically expand on this inequality. So we can say, all right, I is less than or equal to the integral from 0 to pi over absolute value of e to the 2 alpha I r e to the I phi, absolute value over, whoopsie daisy, that's on an angle now. It's terrible. Let's go down. This video is already going to be really long, so we're going to have the absolute value, what was it? Absolute value of e to the 2 alpha I r, yep, r e to the I phi, absolute value over absolute value of this, 2I phi plus 1 d phi. Now this whole thing is less than or equal to the integral from 0 to pi over the absolute value of e to the 2 alpha I r e to the I phi over r squared minus 1 d phi. So that's how we got that bit there. Now, let's take a look at the top of this. So I'm just going to rewrite over here. So we have the absolute value of e to the 2 alpha I r e to the I phi. We can break that up pretty much into like, because you can see up here we have Euler's formula, because if you have e to the I x, that's the same as cos x plus I sine of x. So we can just say the absolute value of e to the 2 alpha I r, multiply this entire thing here. So we have cos of phi plus I sine of, oh, not x, phi. Sorry, I was looking at this one up here. Alright, so phi in here. Now, we're going to distribute this to here and this to here and break this up into 2e. So we're going to have e to the 2 alpha I r cos of phi multiplied by e to the 2 alpha I r times I sine of phi. This is going to turn into a negative 1, so we'll get rid of these i's now because they're in the way. And move the sign a bit closer as well. Okay, now this is all an absolute value box. Now we can distribute the absolute value to just these little parts here. So this little dot here just means times. So I did a little index law, I did a couple of steps at once there. Because if you have a to the power of n plus n, that's the same as a to the m multiplied by a to the power of n. Okay, that's what I did there. So that's how I went from there to there. Okay, now we can do that. We can basically make the absolute value thing only act on this part here, we can make them act on the parts separately. So we'll just say, all right, the absolute value of this whole thing is the absolute value of this first bit here multiplied by the absolute value of this bit here. Now this bit is going to be just equal to 1. Now this bit here, so that bit's going to be equal to 1. Now this bit is going to be less than or equal to 1 because as phi changes, so if we take a look at our sine graph here, because we're only looking at phi from, what was it, 0 to pi, because in our contour up here in our little graph, we're only looking in this region here. So we're only looking at angles from 0 to pi pretty much. So from 0 to pi. That's why like phi has a little restriction on it, okay? So this value here, no matter what you put into it, will always be less than or equal to 1. Okay, and it's got a negative sign here. So if we take a look at this integral here, that's going to be the integral from 0 to pi. This is less than or equal to our absolute value of our integral we're trying to prove goes to 0. Is less than or equal to basically 1 multiplied by e to the negative 2 alpha r sine of phi over r squared minus 1. Now this has a negative sign, so it could go down here. And as r goes to infinity here, this entire thing is going to be equal to 0. So therefore our integral up top, it has to be less than or equal to 0. But for it to be less than or equal to 0, it needs to be equal to 0. So therefore our gamma integral up here, where is it? It's over here. Our gamma integral, as r goes to infinity, this whole thing goes to 0. Alright, so that was the hard part, okay? Now we've sorted this one out, so that goes to 0. Now this part, what are we going to do with this one? So I'm going to move our little diagram here now, because that's no longer, well, it is useful to us, but not specifically now. So we're just going to take a look as epsilon goes to 0 of f of z over the path capital lambda. So what's the limit as epsilon goes to 0 over the integral over capital lambda over f of z dz? Okay. Now, what does that equal? What does that basically mean? So we defined capital lambda as this path here. So it's from negative epsilon to epsilon. So this integral. So I'm just going to ignore, actually let's just move this limit out the way for a bit. So this integral is equal to another integral from negative epsilon to epsilon of f of z. Now, what was it? E to the power of 2 alpha I z over z multiplied by z squared plus 1 dz. You guessed it, we're going to make another substitution. So we're going to let z equal to epsilon e to the I phi. Okay? Now, reason we're going to do this is because we can define it as some term of rotation. Because you notice this little semicircle in here is going to have a radius of epsilon, and this is just a rotation thing. This e to the I phi, it's term of rotation of the angle. So we can make this substitution legitimately. Just need to change the bounds now. So, alright, when epsilon is equal to z, I of phi, so 1 is equal to e to the I phi. Therefore, what's that going to be? I'm just going to do it off the top of my head. It's going to be equal to, so phi needs to be equal to pi, okay, for that to work. And when negative epsilon is equal to epsilon, so that goes into negative 1. Did I make the right choice? No, I didn't. Oops, so this bit here, this one, phi needs to be 0, and this one, phi needs to be pi. I just thought of it in my head because cos of pi is negative 1. Okay, so that's our new change of bounds. So put this and make our new integral. Oh, we also need to differentiate this bit here. So dz is equal to epsilon e to the I to the power of I phi d phi. Okay, so this I came down the front because I is our constant and phi is our variable. So we have the integral from, what was it? Pi to 0 of e to the 2 alpha I epsilon e to the I phi over epsilon e to the I phi over epsilon squared e to the 2 I phi plus 1 multiplied, well not multiplied, substitute for this, dz. So we're going to have epsilon e I phi d phi. This is looking crazy. Alright, so that's going to cancel there. That's going to cancel there, cancel there. We can bring this I out the front, and we can change the terms of the bounds, so we can just move them around. So we'll just, actually, no, we'll keep them the same. So we'll just have I over the integral from pi to 0 e to the 2 alpha I epsilon e to the I phi over epsilon squared e to the 2 I phi plus 1 d phi. Now if we apply the limit as epsilon goes to 0 over this thing, you can see this whole thingy up here is going to be 0. So if we have e to the 0, that's going to be 1. This whole thing here is going to be 0 here. So we're actually going to have basically the integral. So if we apply this limit, we're going to have the integral from pi to 0 of I of 0 d phi, because this whole thing is going to turn to 0 real fast, because this top bit's going to be 1, and this is going to basically be 1 over infinity. No, well, yeah, we're going to have a 0, a 1 at the top here, I think. Yeah, and this bottom bit is going to be a 0. So as this goes to 0, we're going to have 1 over 0 plus 1. So we're going to have the integral of, I admit I'm a bit stuck here. Just need to think for a sec. Yep, so this should go to 1. So if we integrate 1 d phi, it's going to give us phi. Sorry, I'm just checking something real quick. Yeah, okay, cool. So as this goes to 0, we're not going to have the integral. This whole thing, alright, this top bit is going to turn into 1, because epsilon will be 0 up here, e to the 0, 1. This bottom bit, this bit here is going to be 0, but we're going to still have a plus 1 here. So 0 plus 1 is still 1, so it's going to be 1 over 1. So we're going to have basically the integral from pi to 0 of a 1 d phi. So when you integrate that, we're going to have I over phi of the bounds pi and 0. So we're going to have I basically multiplied by negative pi. So that's the value of our integral as it goes to 0. Alright? So what does that tell us in the grand scheme of things? So now we're just going to go to the very bottom and rewrite our whole thing. So we're going to go past everything. So we just put, basically we originally had the integral from over the path gamma, f of z, dz, plus the integral over the path capital lambda, f of z, dz, plus 2I over the integral from 0 to infinity sine of 2 alpha x over x squared plus 1 dx is equal to negative I pi e to the power of 2 alpha. Okay, that's what we've had. So when we applied this limit to make r goes to infinity, this term went to 0, and this term turned into, what was it, negative I pi. So we have negative I pi plus 2I over the integral from 0 to infinity of this whole chunk here, which is our Leibniz integral when it was differentiated under the integral sign, is equal to negative I over e to the 2 alpha. We can cancel all the i's, So we're going to rearrange it. So we're going to have the integral from 0 to infinity of sine of 2 alpha x over x squared plus 1 dx. Move the negative pi to this side, so we're going to have plus pi over here, divide everything by 2. So we're going to have, if you let me think, we're going to have basically pi over 2 minus pi over 2 e to the 2 alpha. Alright, cool. Now we're getting somewhere. Now we established that this integral here, this integral is f dash of alpha. So if we want f of alpha now. So we'll just say, alright, f dash of alpha is equal to pi over 2 minus pi over e to the 2 alpha. Okay? Now our original integral was the integral from 0 to infinity of sine squared x over x squared over x squared plus 1 dx. Now this was f of 1. So f of alpha is equal to this that we established at the very start of the video. This has been a very long video. If you stuck through this, I commend you. So this is f of alpha. So if we want to get f of 1, which is the value of our integral, we need to evaluate this in terms of alpha from 0 to 1, because this will give us f of 1 minus f of 0. Now f of 0 is going to have a 0 here, and 0 divided by 0 is undefined. So this whole thing will be 0. So if we do this integral on both sides from 0 to 1, d alpha, this is going to give us basically the integral from 0 to infinity sine squared of x over x squared of x squared plus 1 dx is the integral from 0 to 1 of pi 2 minus pi over 2 e to the 2 alpha d alpha. And this is when, yeah. Okay, so if we evaluate this final integral, 0 to 1 pi squared minus pi over 2 of 2 alpha d alpha. This term, when we integrate it, we're going to have pi over 2 alpha. If we integrate this, we divide by the differential, so we're going to have plus pi over 4, 4 e to negative 2 alpha, because the derivative of this here is negative 2, and if you divide by the derivative, that integrates it. So so that cancels there to the alpha, and then you put, of course, the bounds on the outside. So this is from 0 to 1, and all we do is substitute alpha for 1, so we can have pi over 2 over 1 multiplied by 1 plus pi over 4 e to negative 2 to the 1. So we're going to have our answer is equal to pi over 2 plus pi over 4e squared. Now that is equal to this integral. This is the longest video and the hardest integral I've ever done in my life. Thank you so much for watching. If you have any questions at all, leave some in the comments. See ya.